All right. Okay. Make sure. Yeah. Okay. Welcome back. Yeah. So we're gonna do it like today. So the plan for today is that since we did the blackjack last time, so I guess I'm not sure. Like, okay, I'm gonna do a little bit like review or like about the DP first, and then we're gonna go to the problem we're gonna do today, which is the longest palindrome sequence. And this problem is also DP, so hopefully we have the time to code it out. And because like for the previous two sessions, we don't have any time to like do any coding. And for dynamic programming, it's just like theoretical. All we did was pure theoretical. So hopefully we got like for this time we have some like chance to actually code it out. And if not, we're just gonna. But before we code it out, we're actually gonna like walk through like each of the steps for doing the longest palindrome sequence problem. So, okay. So, all right. I'm gonna do a little bit brief review of what problem we did previously. So let me think of that. Yeah. Okay. Yeah. Let's go to the perfect formation blackjack first. All right. So just do a little bit of review. I know that last time we also covered this problem, but I just want to do it a little bit more like thoroughly this time. Okay. Yeah. Okay. So the problem is that we have the problem is called blackjack. So basically okay. So the problem is called blackjack. It's basically okay. So we're just getting started now. So we're basically gonna do the little bit review of DP and then go to the problem. Yeah. Okay, so the problem is called blackjack, and basically you have a deck of cards. Okay, so it's not gonna be like the one you can use in Vegas though. Like it's not that practical. So it's just like a DP question. So we have a deck of card, and it's gonna index from C0 all the way to C51. That's how many cards there are in the deck of cards. And that's the first part. And the second part is that we're dealing with the situation that's one player versus one dealer. One player versus one. Yeah. So one player versus one dealer. So who here has played the blackjack before? Okay, one person. Okay, I'm gonna go briefly over like what the rules are. So like in blackjack, basically another name of blackjack is that it's called 21. So basically the rule is that you're gonna play with the dealer, right? Someone who's from the casino, and you're gonna be the player. So so the rule is that very simple. So you have a deck of cards, right? And at first, the dealer will deal with him. Like you have the dealer. You have your, like, this is you. So the dealer is gonna give himself two cards first. And these two cards were from the top of the deck. And after that, the dealer will give you two cards. Right, so far makes sense, right? And the rule is that, okay, the reason why it's called 21 is because you want to get close to these points as close as possible. Right? You want to get close to 21 as close as possible. So in other words, like, you have dealer has the points, which is just the sum of these two cards. And then you have two cards, and you can sum up these two cards. And let's see, if you got 20 points, right, and the dealer got 19, you basically win because you get closer to 21, right? And after that, the rule is kind of interesting because so far everything is deterministic, right? I mean, I say deterministic because you don't have any degree of freedom so far, right? Basically, the dealer gives you cards, and then the dealer gives himself two cards, and then gives you two cards. And so far, you don't have a degree of freedom, and that's where the game begins. Okay, so right now you have a choice now. So the choice you have right now is that you can either choose to hit or you can choose to stand. All right, so what does this two term means? So when you hit, the dealer basically gonna give you another card. Right, you have a third card, your third card now. But if you choose to stand, the dealer just gonna give you just have these two cards. That's it. And you're gonna make the comparison with the dealer, how many points you have. Okay, So if you but okay, so the reason why it's interesting now is because even though you have a third card, you have a higher chance to get closer to 21. The risk is that you can't actually exceed 22. Sorry, you can't actually exist 21. So the highest point you can get is 21. If you exist that, you basically just lose automatically. Yeah, that's the rule. Like that's why it's interesting. So you can't actually hit forever, right? If you hit once you get over 21, you just the game is just over. All right. So okay. So does the rule make sense so far? Okay. So yeah. So this is like the two rules. So the first one is that the deck is from C0 to C51, just to make it generalized. And the second part is that it's one player versus one dealer. So in the real casino, you can play multiple players with one dealer, right? The dealer is always going to be one, but there could be multiple players. But for the simplicity of the game, we're just going to assume that it's one player, so you versus the dealer. I think you can also implement some other algorithms that deal with multiple players with one dealer. But the case is going to be more complicated. So for this problem, and with the DP, we're just going to deal with one player, one dealer. And the third part is that we want to assume that it's always $1,000 per bet. Okay, so actually not a bet. So what does this mean? So this basically means that each round you play, you're gonna give it into $100. Sorry, $1,000 as your as money you put into the pool. And so what it means is that each time when you play a hand or when you play a round, it costs you at least 4 cards, right? The dealer has 2 cards, and you have 2 cards, and you can ask you for another card and or even more cards. But at least it's going to cost you 4 cards. So the game ends when the game ends when all of the cards are ran out. So it doesn't matter how much money you have. You can have as much money as you want. So the game only ends when all of the cards are ran out. Does this make sense? And also we don't allow any shuffle here. So which means that the card is also deterministic. Okay, so the DP problem is that so basically the DP problem is that we're gonna assume that you know all of the cards beforehand. Alright, so before doing that, I want to do a little do a little bit of brief review of what we covered previously about DP, right? So before going into that problem, this problem is not easy, first of all. And we want to go over something beforehand in order to talk about this problem. So I want to do a little bit of review of what we talked about previous class. So remember that there are 3 types of the DP problems. We'll cover 3 types today. At least as far as I know, there are 3 types I have encountered. I'm sure that there are more, but basically most of I would say probably 80% of the DP problems, not necessarily the most challenging one, can be categorized into these 3 different categories, classes. So the first one type of DP problem called a suffix problem. And the second one is just prefix. And the third one is, doesn't have a really nice name for this third one, but it's just gonna call it IJ. Okay, so the reason why they're classified in this way is because if you look at the first problem, we can denote this problem as using Python notation, which is exactly what suffix means. So the first one is I comma, and the second one is comma I. Okay, so what does this mean? Okay, let me bring you to the first of all what each of this means. So far we have solved some problems, right? And one of the problems we have solved is called tax justification. Okay, so tax justification. Okay, let me remind a little bit what this problem is about. So this problem is about this is also a DP problem, and it's giving you a long list of words. Right, it's a long list of words. And it's asking you to split this list of words into several lines. So basically imagine you have a Word document, and you're trying to make the split of this long list of words such that when they are split and put on different lines, they look as nice as possible. And more specifically, you have a cost function associated with how nice does it look, which is a map you can keep track of. I'm gonna skip the details now, but I'm gonna go over like why this is the suffix dp problem. So the reason why this is a suffix dp problem is because each time you make a decision where to cut the line, right? You basically just solving a problem that's okay. You can always Let me say it this way. So you start with the first word, right? That's the first word is always gonna be the first line, right? So this first word, without any doubt, is gonna be on this spot. So you know where it will start. So the only guess you will have is where it will end. Does this make sense? So you want to determine where the line like starts and ends. You know where the line starts. So the only guess you have to make is where it ends. So you want to make a random guess where it ends, and you want to put this whole segment where it ends and where it starts into this one line. And from there you can get a sense of what the cost function would be. So the reason why it's called a suffix problem is because so each of these terms, suffix, prefix, and ij, is based on the way you define the subproblem. Okay, so what is a subproblem? So in this case, the subproblem is that each time you make a guess, right? So the subproblem basically becomes the thing that you have at the rest of the thing you have. So in this case, you make a guess of this. So this would become the first part of the sentence, right? And after that, those parts will be the subproblem. You have to keep guessing like this. So right now, this will be the start of the word, right? After you guess that this will be the first line, so this will be the start of the second line automatically, and then you have to guess where the end of the second line will be. So that's a subproblem. And the way it's called a suffix problem is because okay, so look at the word. All right, so the word suffix means that so let's say we have a word that's imperfect, right? I know this is a little bit confusing right now, but hopefully each of this will make sense. And the reason we categorize them is because once you see that if you're able to categorize what type of dp problems this is, the cost function or the state transition function is pretty much the same. You can just learn one and then get a sense of what the rest of it will be. So just look at this word perfect, right? So what is the suffix of perfect? It could be just this part, right? It's just FECT. Basically any part that ends at the end with T, right? That's what we define to be the suffix. And also ER's FECT, it is also a suffix of the word. So a prefix will just be PER, right? This will be the prefix. So suffix means the end. Prefix means the beginning. And IJ, just you can imagine why IJ is different from the previous two, because IJ is basically saying that you start with a random place, let's say the second character, and ends with the last second character. And this will be called IJ. So that's how it's different. So, so this is the word, what does suffix means when you put it into the syntax of a single word. And now we're going to see why this dp problem is called suffix. And the reason is because each time you make a guess, the subproblem you have left with is always ends at the end. And correspondingly, what would be a prefix problem? So the prefix problem would be that you start with the end, and you solve the problem from this end. So each time you solve the problem, but the part you end is always at the beginning. The subproblem you end is always at the beginning. Okay, so yeah, hopefully that makes a little sense. But the point is that text justification is a suffix problem, and we're gonna see why that matters in a second. Okay, but that's what the DP is about. So just remember that try to categorize each DP problem you see as either of these three problems. Okay, so before just one more thing before we go into how to solve that problem. Actually, I'm gonna ask you how to think about how to solve this problem in a sec, but I'm gonna define some terms first. Okay, so I said that for DP, the hardest part of solving a DP problem is that you need to figure out two things. So the first thing is that what is a subproblem, and the second part is that what is a guess. figure out what the subproblem is. You need to figure out what the guess is. And then there are two ways to implement the DP, right? One way is that you can use recursion plus memo table. Or you can use like a loop plus the DP table. By the way, the DP table and memo table, they're the same thing. So the first thing that you define the subproblem and you try to make the guess. Third part is that you try to use either of these two approaches. Either use the recursion with the memo table or you use it with the loop and the DP table. Yeah, does it make sense? Okay, I know it doesn't make sense. Alright. Okay, let me try to make it a little better. Okay, better than this. I know that some of you didn't actually attend the previous sessions, but I'm gonna try to make this as clear as possible. Okay, so I know that some of you might heard this term that's recursion, right? And the other one is a loop. So let's think about what's the difference between these two approaches. Okay, this is actually the hard part of it. So okay, let me think about how to do that. Alright, so one more important thing for thinking about the DP problem. Okay, so remember that in the Fibonacci number, how many of you have solved the Fibonacci number problem before? Yeah. Have you seen the Fibonacci problem? Fibonacci number problem? Yeah, so Fn is just equal to Fn minus 1 plus Fn minus 2. Right, this is the Fibonacci number. Right, so okay, so I'm gonna erase this part, right? Okay. Yeah, I said this part will leave most of this part, how to solve this problem by you. So that's the challenge we have today, that we're gonna make things work that you actually understand how to solve this type of DP problem. So I figured that it's gonna be really inefficient if I just say each time that how to solve this problem. Actually not work very well, but yeah. Alright, let me try to make each of this part first make sense. Alright, so remember that this part, right? Okay, now what I'm gonna do is that I'm gonna represent each of this part. So the subproblem, the guess, and okay, let me add a little. Sorry, this is the fourth part. The third part is related subproblems. So the first one is the subproblem, second one is the guess, third one is the related subproblems. So, what do I mean by related subproblems? So normally this is just a mathematical formula, right? This is actually a formula that relates all the subproblems. Because you can see that, so the problem for the Fn, which is the final problem we're trying to solve, is dependent on the previous two problems. So this mathematical formula gives us the way to relate each of these subproblems. Does this make sense? Right. And for the shortest path problem we had previously, we used actually this kind of a okay. I'm actually not going to this part. It's a little bit complicated. But we're gonna see that okay. So there are two ways normally to relate the subproblems. One way is using this, and we call this a transition function. So it's called, more specifically, it's called a state transition function because each of this is a state or a subproblems you have computed before, and you're trying to relate the subproblems with the solution you're trying to get. Okay. So this transition function either in the form of a math formula or it could be a logical loop. Sorry, not logical loop, but logical condition statement. Yeah, we're gonna see this case in a while, at the end of today's session. Then we're gonna see one example of this. This could be a type of transition function, and the other type is just the math formula. Okay, and when I say guess, I mean that okay. So yeah, I know some of it didn't come previous section, but okay, never mind. Okay, now what I'm gonna do is I'm gonna try to write each of these, represent each of these components on a graph. Alright, so it makes it very intuitive. But more specifically, I'm gonna use the example of the Fibonacci number. So what I mean is that so how do we solve the Fibonacci number? So if we you see from the recursion case, right? We start with the recursion, which is fn, and we split it up into different like subproblems, right? One is the fn minus 1, the other is fn minus 2, right? Does this part make sense? Okay, so okay, and the last part is you just split 4 until you reach the base case. Right, so each of these would be the base case. Right, so the recursive way to solve this problem is that you just go from the top, and then you split the base case each time until you reach the, you split it each time and then you go to the base case eventually. So this is the way we solve the recursive way of solving the Fibonacci number. Now, like, what would be the other way, that loop plus DP table way? Like, what do you think is the other way? Any idea? Go from what? Sorry.
From the bottom.
Yeah, exactly. Right, and that's actually quite amazing. Let me say a little bit like why would that be amazing? Okay, but exactly this time we go from the bottom. Right, so the bottom will actually just be f0 and f1, right? Because f0 is just the base one of the base case, the other one is f1, and then we can compute what? F2, right? And then after that, we can compute f3, which is just f1 and f2. And then after that, just going upward until eventually we reach fn. So does this make sense? Any question? Okay. So the reason why this is amazing is because if you compare these two different approaches, you're gonna find that they're actually symmetric. So this is why it's beautiful, because I said there are two approaches to the DP. One way is that you use the recursion and positive member table. The other one is the loop and DP table. You're gonna find that these two ways actually symmetric to each other. One way is just that you go from the top to the bottom, and the other way is just from bottom to the top. That's why you see that sometimes when you do solve the recursion problem, you always have this one loop first, like at the head, which tries to like compute all of the base case first, and then the other loops are nested, which is going like upwards in the recursive case. That's what often happens. But computationally, they are always the same, like on this graph. So it's always useful to think about this graph when you're trying to solve the DP problem. And the reason is because you don't want to encounter any case like this. So I think this is called. Do any of you remember what these things are called? Okay. Like DP term.
Member table.
No. Member table. Yeah, I mean member table is like kind of memorize each of these states. Arrays. No. Like what each of this is called. Okay, it's called that. No, I'm sorry. I didn't phrase the problem like the way very well. This computational graph. It's called a DAG.
Oh, data cyclic graph.
Yeah, exactly. So this is a directed acyclic graph. And it's always useful to think about this way. The reason is because you can always check if you have any problem. Okay, let's see. Let's see why is this useful. Okay, so you don't want to do your DP in such a way, right? Does this make sense? You don't want it to be cyclic. And the reason why you don't want it to be cyclic is that you're trying to find the answer of the fn, right? But you go to this part, which could be I don't know, n minus 4, but maybe. Okay, so right now you have fn minus 4, and you're trying to solve fn minus 4 using fn, right? In this case, so this becomes a cyclic graph. So this would actually be what? What do you think this would be?
You would run for it.
Yeah, exactly. This will be like an infinite loop. So it's always useful to think about like, is your DP constructed in the right way, or specifically you want to do it in the right order. Right? You don't want to encounter this kind of problem. You don't want to do this kind of like cycles. So okay, I said that this kind of a directed ABC graph is can represent each of these different components. Okay, so what is each of the node? If you think about it, each of the node is actually just a subproblem. Okay, so or we can call it the state, computational state or the node. And the gas is just each of these, from each of the node, we split it, right? We split it into different branches. Oh, actually, in this case, it's not really gas. But maybe this is not a really good example of the gas part. But we're gonna see that what is for the Bellman-Ford algorithm, which is we covered like in the first one for the DP class, we actually have a perfect example that what it will be a gas. Gas just not a really good example here. But anyway, okay, I'm gonna move forward to the next part first. Okay, what do you think is the third part, like the relate to the subproblems? What do you think is that part, like on this graph? Where does that lie? So it could either be a logical condition or like a mass moment, or it's actually called state transition function. What do you think is like corresponds? Where is it corresponds on this graph?
Is that the edges?
Yeah, exactly. So the edges are actually the transition functions, right? So that's why it's so useful, because if you see this chart, right, whenever you see a DP problem, just think of this chart and you try to figure out what each of these components corresponds to the problem. So you try to think of first, what is the subproblem? What is each of these edges? And that's easy. That's not really the creative part, because you can define the subproblems in a variety of ways, right? You can define but sometimes depending on the type of subproblems you define, the problem can be hard or easier to solve. That's also the tricky part. That's why it's so artistic. And each of these nodes is just the subproblem, and each of these edges is just the transition functions. So which is why that each time you try to solve this problem, you try to jump to each of these substates. That's why it's called a transition function. And correspondingly, okay, so we're gonna see that each of these edges, on both cases, is exactly the same. So the transition function for the recursive approach and the loop approach is exactly the same. These edges, the properties of these edges on both graphs are shared. So always think about this kind of graph, and those three different what each of this means when you're trying to solve a DP problem. Okay. All right. So yeah, and also when you're trying to define the subproblem, you always think about what type of a DP problem you're solving, whether it's a prefix, suffix, or IJ problem. Either of those. Any of those three different types of subproblems. Okay, now we go into the real challenge now. Okay. So far, any questions?
So will this Fibonacci problem will be defined as like a prefix?
You mean like the Fibonacci number?
Yeah.
Oh, let me think about that. Would it be a prefix problem? Actually, what do you think?
I think it is a prefix.
Why is that?
Because
yeah. Okay, so let me try to understand if this is what you think. Okay, I'm trying to think okay, you said this is the prefix problem because you are thinking the way that it's working backwards. Is that what you think?
Yeah, I think
so. So you start with Fn and then you go a little bit backwards each time. So the part on the left way is always start with the front. That's why you call it a prefix problem.
Yeah.
That's correct. That's correct way of understanding it. But I would say that the Fibonacci number problem is literally the easiest problem you can solve in DP. So you don't have to care too much. I mean, this one can be either a prefix problem or a suffix problem, because you can just start with the front first, with the base case first, and then build up the DP, right? Build from the bottom to top.
Yeah.
So that way it would be a prefix. So that way it would be a suffix problem instead, right? So it doesn't. But anyway, it's not like an IJ problem. That's what's important.
Yeah, I see.
Yeah, but yeah, Fibonacci problem is really easy, sort of. So you don't have to care too much how to define it. Yeah, the real challenge is when you encounter a problem and it's really hard to see why it's a DP problem. You want to try to put it in each of those three slots and see which one works actually. And that's actually what we're gonna do right now. Yeah, so if you don't understand any, if you don't memorize anything, just try to understand what that graph looks like. And that's actually gonna be really, really important. Actually, I took a bunch of DP courses before, and I found the most effective way of thinking DP is using that graph, surprisingly. Okay, we're gonna see that graph over and over again later. Okay, so now we go to the real problem. So I want you to think about this problem. Okay. All right. So any question with the blackjack problem?
Does the dealer get to hit instead?
No. We assume that dealer never hits.
Okay.
Yeah. So he always has 2 cards. So the only degree of freedom is on your side.
Okay.
Okay. So the goal is that you want to maximize the profits after the game ends. Before going to how to do the DP problem, I ask everyone a question. So, why do you think this for this problem the greedy approach won't work? Any idea?
Like if you try to win this round, then you might have like bad cards for the next round.
Right.
So
Exactly. Yeah. Anyone understand what that? Okay. Yeah. I'm gonna say exactly one more time. So what that is? Yeah. So the reason why greedy algorithm won't work in this case is that greedy algorithm always try to do things locally optimal. So it's always locally optimization. So local optimization in this case means that you basically try to win this round and this round only. So that's cool. That could be beneficial, like at first, right? And I mean, you can win the first few rounds in a row, and then basically you find that you basically run out of luck somewhere, right? Because you got all of the good cards first, and you don't think about what happens later, right? That's what basically greedy algorithm does. So it doesn't consider anything besides this round. So that could be a problem when you win this round, when actually next round you actually lose, or you lose several rounds in a row. That would be why DP problem won't work. Because we're trying to optimize the we're trying to optimize globally, not locally. So I said that the problem is maximizing profits when the game ends, right? That's what globally means. Not really when each round. That's why DP comes to place, not too greedy, not use greedy. So but always in trying to solve a problem, you always try to think about the greedy approach first. Because the greedy approach is simpler and it requires a little bit of math to prove that the problem is of greedy nature. But once you prove it, the problem can be solved very quickly, and it's often just a very linear time something. But whenever you have a problem that's not greedy, like this one, I mean you always want to ask this question: that does greedy algorithm work or not? But if it doesn't work, you want to always try dynamic programming, because very rarely do you actually encounter any brute force scenario that you just use brute force to solve this problem. Unless this problem is an NP hard, right? Anyone understand what NP hard is? Or NP problem?
it means you can't solve it in
Polynomial time. Yeah, exactly. So unless this problem is NP hard, you can solve it in polynomial time. You have to use brute force. And one big sign of what that type of problem is that when you look at the scale of the input, right? It's normally just lower than 10 to the power of a third. It's definitely lower than that. It can't be more than that. If it's more than that, it requires log n complexity or almost linear complexity or quadratic, but it can be 10 to the power of fifths and something like that. So it's normally just 100. If that's 100, then just feel free to use brute force. Otherwise, just use DP. If you don't see how the problem can be solved using DP, then basically you have the wrong subproblem defined or the wrong gas. These are those 3 components you didn't do it well. But most of the time, I'll say it's like UCPP. That's it, like pretty straightforward. It's actually very few choices to choose from. Yeah. Okay, with that being said, okay, so let's work on this problem now. Alright, so any idea like how to think of this problem?
Can I ask something?
Yes.
So, what do you mean, like, when you say we know all the cards? Does that mean, like, every round, like, in every round, do we randomly get 2 cards?
Okay, I see what you mean. Okay. Yeah. Okay, so let me restate what this means. Okay. So before you play, right? Before you play, you have 52 cards. And you know what those 52 cards are already.
Okay.
And it's not gonna be shuffled.
Right.
Yeah. So you have a like an inside man from casino. Does it make sense? Yeah. Any idea like how to deal with this problem? What do you think is the cut, like the thing that really optimizes here? Or any idea? Okay, I'm gonna give you a few minutes. Okay, try to think about the thing we have covered before, like what type of problem this is, what's the each of those components, and yeah, what are you really trying to optimize here? Like, how do you really optimize? Okay, any idea?
Is the goal to win like as many rounds as possible?
It's a goal. What do you mean by goal?
Yeah, like what do we want to? Are we trying to win as many rounds?
No. We're trying to get as many profits as possible. So each round you have $1,000. And you can okay, so if you win, you get $1,000. If you lose, you lose $1,000.
Oh.
If you tie, you just get zero.
Oh, okay.
Since they never been to casino. I mean, I never been there either.
So, like, so if we get, looks like we get 2 cards at first.
Right.
Do we know do we know what the next card is?
Yeah, you do. Because you know the whole deck.
Okay.
So how does the dealer deal? Like, does he give himself 2 cards and then you 2 cards, or does he give himself 1 and then you and then?
No. Dealer always has 2 cards. Alright, so the blackjack rule is simple. Okay, so I think I overestimated the simplicity here. Okay, so basically dealer gives himself 2 cards first. And that's it, like that's it for him. His play is completely deterministic.
Oh, like he has the same 2 cards for every round.
Right.
Oh,
You
okay.
can just imagine dealer as a robot.
Oh, okay.
Yeah. His play is completely deterministic. No strategy at all. Yeah. I mean, if there's strategies, that would be scary.
And we do know what cards he has, right?
Yeah, you know every card. It's kind of interesting to think about, like what happens if dealer has a strategy. Okay, any idea? Okay, I'm just gonna ask some questions here. So what do you think is the thing that's really up to you to choose in order to win the game? That's a very important question, right? Because
Whether
you're
you
trying to
hit
win.
or not.
What's that?
Like whether you hit or not.
Yeah, whether you hit or not. That's very good. Any other idea? Okay, I'm gonna write down what you said. Okay. So you said that the only thing that's up to you is whether you hit or not. Okay, that's very, very good. Okay. But I'm gonna expand a little bit on that. So let's remember that the question you asked is whether you hit or not, right? Okay, so let's walk through a little bit, like, why is this the case? So try to, while I try to walk through the game, try to think about like which part is deterministic, which part is not deterministic, which part is up to you, which part is involves degree of freedom. That's really the important part of the game, right? The dealer gives himself two cards, right? And that's always deterministic, right? And let's say the current card is the C, let's say CA, okay? And this part becomes the CA plus 1, right? And there's two cards can give you, it will be let's see, CA plus 2 and CA plus 3. Yeah, I'm just trying to use this alphabet to make it generalized, but it's just don't have to think too much about that. So these are the 2-4 cards, right? And after that, the thing that's really up to you is for you to ask yourself that do you want to hit or do you want to stand, right? And that's it. And if you want to hit, the dealer will give you another card, which is CA plus 4. If there is another card, okay, give it. So and after that, it's gonna be CA plus 5. If you hit again, right? And if you see that okay, you have cards that just the sum of them is more than 21, you can't hit anymore because you lose, right? That's really the part that's up to you. So do you see now the question you should ask yourself is whether you hit or not, right?
Yeah, so I think like
Yes.
so like in each, for example, in one round, you know like the maximum number of cards you can have. Because you know what the next card is, and you can
exactly.
calculate how to for the sum to smaller than 21.
Yeah, so that's the constraint, right?
Yeah. So for example, you know that you only can do 4 cards.
Exactly.
Like,
Yeah. Right.
Then you can like calculate.
Yeah.
So you can check the maximum between if you hit or not.
I see. Yeah, that's the number. That's the gas you can have, right? That's the range of the gas you can have. Let me just narrow down what you said. You say that okay, so because you can't actually go above 21. So the gas you can have, the number of cards you can hit, like that's basically the gas part, right? The gas part is really how many times you hit. Okay, let me rephrase that a little bit. Oh, that's very, very good. But I'm gonna go to that part right after. Okay, I'm gonna say like make a little bit comment on the question you're asking here. You're asking that whether hit or not, right? But if you think a little bit, like that's actually not a really, really good question to ask. And why is that? Because each time you ask whether hit or not, you're making a guess that has 2 possibilities, right? And if you hit or not, you try each of them. And next time you also try each of them, and next time you do each of them. That's exponential, right? Each time you have 2 possibilities. Each time you ask yourself this question, you have 2 choices. That's 2 to the power of n, right? Where n is the number of cards. You can hit as many times as n, right? To like just say worst case scenario. Like don't consider like hey, if it exists 21 or not. You can hit n times. That's gonna be to the power of n. But that's actually a really bad question if you think about it, because you're trying to use DP. The whole point of DP is that you avoid the exponential, right? So what would be a better way of asking the question? It's not whether you hit or not, it's how many times you hit, which is a continuous and includes 0. That's actually a better question because, okay, let's see why that would be a better question. So if you ask yourself how many times you hit, so this is like a discrete number, right? It could be range from 0 to 52. Right? You can hit no cards, or you almost can hit 52 cards. But the difference is that this time you only have to try 52 different possibilities. And it's basically just an n, right? N is the number of cards you have. But in this case, you try to the power of n, which each card you ask yourself whether you hit or not. This is more possibilities, right? So this is a slightly better question to ask. Do you agree?
Yeah.
Right, and that's why, like, say, DP is so have so many ways of asking this kind of questions when you design the DP algorithm. It's really about design. It's not about like the other things. So depending on the way you design the algorithm, your complexity is completely different. So in this case, you want to ask yourself how many times you hit, and this will be the guessing part, right? Because literally, you're guessing that how many these cards dealer will give you. That's the only part that's up to you. Everything else is just completely deterministic. Does this make sense? Make sense? Or wait.
So you're saying like we should do like DPI would be the maximum profit if we hit I times?
Okay. So okay. You say that DPI. Okay. Yeah. Okay. So you're trying to define the subproblem. Am I doing it right?
Yeah.
But do you think that's really okay? Yeah, that's also another thing we had to go over. But do you think that's a really good subproblem, or it's just one of the possibilities?
Yeah, I think it's just a one possibility.
Yeah. What else design you think there will be to make this better? Remember that we said that there's 3 types of problems you can define a subproblem, right? The suffix, the prefix, the ij. Which one do you think it is? You can random guess.
I think it's prefix.
And why is that? It's
Because
close though. Yeah, just why is that, please?
like one solution I can think of is like we store like the base, like the number to hit that is based at this number of cards. So for example, like once 10 cards have been played,
I see.
how much profit?
That makes
can you
sense.
get? Yeah,
Right.
that kind of thing.
Okay, yeah, both of those are valid, but okay. I think if you go down that way, that actually might work. But I'm gonna say that the way we define plot problem here is using suffix. And okay, let's try to draw some similarity here. Okay, so so we have a deck of cards, right? And the reason why it's called a suffix is actually pretty I would say it's make it as simple as possible. Alright, so the reason why it's a suffix problem is because each time you deal with a card from the top. Right? So the bottom part remains the same. And it always gives you a card from the top. So the cards give you those ones. Okay? So you might see that the suffix part never changes, right? So that's the main the goal you want to have when you're designing a DP problem. So that's how what I mean by suffix and prefix. You want to see what part doesn't change, and that part will be in this case will be the suffix, right? And prefix will be okay, let me think, let's say what would be the prefix, if you think about it this way. If the dealer gives you the card from the bottom, that would be the prefix, right? Because the first card you give is really 1, everything doesn't change the front, the prefix part, that would be a prefix problem. But in this case, okay, the dealer always gives you from the top. So it would actually always be a suffix problem. Does this make sense? And the reason why it's important to think in the suffix problem or the prefix problem is because, so you don't want to go into ij as much as possible because the ij involves 2 different variables, right? I and j. But the suffix and prefix problem is always just involve 1 single variable, just I. And in this case, we want to use I to define how many cards you have. What is the index of card you currently have? So DP0 means that you have the whole deck. You want to use DPI to record what state of game, what is the state of the game you're currently at. And what is keep changing, number of cards, okay? So if it's DP0, it will mean that you have the whole deck. Because the card you're going to have is 0. So that's what DP0 means. And DP1 basically means that you have used the first card, and you try to, the subproblem you have is just from 1 to 51. That's the suffix part. And DP2 is just from 2 to 51. That's the suffix part. So this part is just you can imagine this as the index of the suffix you currently at. That's what a suffix means. You have to feel what it means to be a suffix, right? The part that remains, right? You're not using one index to indicate which part it remains. And the same is for the text justification problem, right? You have a long list of text, right? Each time you make a cut, some part of the text remains, right? This part always remains to be the same. you see, like, you draw some similarity, you feel like these two different problems are quite similar, right? The suffix always remains because each time you make a cut and put this one line, the part that remains always ends at the end part of the text. So the ending part is always the same. That's a suffix problem. So both of these two are suffix type, both of these two types of problems are suffix. So you can use like this DPI to indicate what part of suffix you currently have. If that makes sense. So in this case, okay, DPI will indicate that, okay, so DPI would just record that how much profit, what's the maximum amount of profit you can have when you have I being the current index of the suffix. So DP0 would simply be the solution of the problem, right? Actually no, not DP0. DP51 would simply be the solution of the problem. I mean, actually, let's not go to that part. But DP51 basically means that when you are currently at 51's card, which game basically ends, right? So that would mean that how much profit you can make, from that point. That would be the end of the scenario. Does that make sense or not? So DP, you also want to ask this question, now what does DP denote? So here in this case, DP denotes that at the suffix of the problem that when the index at, the suffix at index I, what's the maximum amount of profits you can make? Does it make sense? Yeah, I suddenly feel like an econ class. Okay, so, alright, so that's the subproblem, right? The subproblem is just how much cars you have left. What's the suffix condition right now? That's the suffix, let's see what we have here now. So we have the subproblem, we have the guess part. Guess part is just how many cars you want to hit this, at the current subproblem. Does that make sense? So you see you have 51 cars left. You want to make a guess at how much cars you want to hit, which could be range from 0 to 51. Potentially, right? Except when you go further, you just lose the money. But that's also a possible scenario. Does that make sense? Yeah, so guess is the question that how many times you hit. Subproblem is what's the index of the suffix you currently at. Now we have the last part left, which is how to relate each of the subproblems. Okay, I'm gonna write this one down because this one is literally the least abstract part we have to understand. And I'm gonna write it down first before saying anything about this part. This part is also very important. Alright. I'm gonna write down the transition functions, which is DPI, just equal to maximum. So this is the transition function we're gonna have. I know it doesn't make sense so far, okay. But the point I was trying to make is that this part is very important because once you identify that this problem is a suffix problem, you're gonna see that the form of the transition function is shared, or at least it's very similar to each other, in the way that all you have to change is the max, which, okay, so remember that when we were talking about the text justification problem, right? The part that's changed is we were doing the min instead of max. Because when we were doing that problem, that was the penalty cost problem, right? So you want to minimize the penalty. But in this case, we're doing the the problem we're solving is maximize the profits. So in this case, we're trying to maximize the profits. So this is one part that changes. And the other part it changes is that, okay, so this is the current run. So this part, outcome is from a set from that, like this set. So this set basically indicates that what's the result of this current run. So you can either like lose $1,000, you can win 1,000, or you can tie, right? This has 3 different outcomes based on the J you choose. What does J mean? Anyone have any guess what J mean?
The number of time you hit.
Oh, actually close, but J actually here means that, okay, so remember that dpij means that like the state, right? Okay, so J minus I is actually the number of times you hit. J means that after you hit this number of times, J minus I times, you are going to the J state. Right, because you basically use J minus 1 cards, and then you just the next card you have is just the dpj. So this is why it's like I wrote it this way, like the for loop here is basically trying to guess all of the possible scenarios here. So the for loop basically corresponds to the guess part right there, like the second part. So in which case I'm saying that for all of the J minus I in the range of from 0 to 52, this is basically saying that the number of times you can hit is a range from 0 to 52, right? That's all the possible ranges you can have. And this, like this loop is why it's only costing you O of n, right? Instead of exponential time, the first type of question we're asking, like instead of asking that whether it hits or not. And this is like the for loop is also just correspond to the guess. So you're gonna see this form in 3 different components. So one component is that you're trying to maximize or minimize. And the second component is that what is the result of this current run. And the third component is that it's guess function. Right, so each of these 3 will vary, but the whole structure for the suffix problem it's always the same like this. That's why it's always useful, I think, to categorize them into suffix, prefix, and ij problem. But each of those forms will be different, though.
So,
yes.
Can I ask, this means that J has to be greater than I, right?
Let me think about that.
So should it be
Yes,
like,
it means that.
So should it be like dpj equals to...
Let me think about that. Oh, actually, I know what you mean. Okay, so yeah, I actually made a mistake. So C0 basically means you have the whole deck, but actually you're trying to build from the bottom, right? Actually, let me think about that. Okay, what would be the base case? Like you think? What do you think should be the base case here?
It should be... So before we say that dp like 51 would be the answer. So basically it should be dp 0.
Let me think about that. Right. So what does dp0 mean? So at the when you have the whole deck, what would be the possible profits? And versus to when you have no cards, what would be the profits? Yeah, that makes sense. Okay. Okay, so that makes sense, right? So dp0 means that when you have the whole deck, at which point you don't have any like profits, right? So dp0 should be 0, right? You don't make any profits from there. And let me think of that. Okay. Actually, wait. Okay, so actually, okay. So on my note, actually I define dp probably in different ways. That I actually start from the bottom. So I define dp notation using that how many cards you have left. So dp52 would mean that you have 52 cards left. But it's actually the same. But the point is that dp0, dp1, 2, 3, 4 should all dp0, 1, 2, 3 should all be 0. Do you understand why?
Yeah, I see.
Because those are all on the first run. We haven't made any money, so those are all base cases, right? So that's like the base case. Yeah. But okay, so this is the same here. So basically, you're going from dp0 all the way to 51. So 0 are the base case. These are the eventual answer. 51 is the answer you want.
Yeah.
Right. And in this case, okay, let's think about that if this makes sense. So then this would be right?
I thought this would be like the definition if you have dp I is like you have I cards left.
Right.
So this means that DP0.
Oh no. This is actually using the notation we can currently do. Like DPI basically means that you have your currently ice card.
Okay.
Yeah. So this will be this will make sense.
Yeah.
Right. So this is okay. So this is does it make sense for anyone or everyone or any question? Any question for Jane? Okay. Any question? Okay. Okay, cool. So I want to, okay, so just after that, I said that we're gonna see the directed acyclic graph again. So let's see how that works here. Okay, so let's see how directed acyclic graph works here. So you have so we define the subproblems, right? Define the subproblems as the number of, in this case, the subproblem will be that the index of the current suffix problem. So the bottom case will be that we have a 0, right? We got at the first card, and for a second card, and third card, and fourth card. Sorry, so all of this would be the base case, right? From which you don't make any profit yet, right? Because this is still the first round. Oh, actually, let me think. No. DP3 will be not. 3 will be when you can hit. 3 is the part where you can actually choose to hit or not. I mean, this is first dealer's card, second dealer's card. Third is your first card, and fourth is their second card. Yeah, actually, this is the part that's base case, I think. So among all these situations, the game hasn't begun, right? Because you need 4 cards to begin the first round. So in all of those cases, the base case is just 0. Does it make sense? So the fourth card is the card that you can choose to hit 0 times. So the fourth card basically means that you transition from 3 to fourth card when you have the guess that you basically hit 0 times, right? Because the fourth card actually again begins. And if you choose to hit, let's say, once, that would be basically mean that, let me see for that. So you can either choose to hit twice, you can either choose to go from 3 to this time, right? Where you hit once, or you choose to hit 0 times. Okay, actually, yeah, right. Go 3, 4, 5. This would mean that you hit once. Let me think on that. Oh, actually, I think this is okay. So if you hit 0 times, basically from 3 to 4, right? And if you hit once, it's just from 4 to 5, right? And if you hit twice, just from 4 to 5, 6. Does it make sense?
Yeah.
Yeah. If you hit twice, if you hit once, it's just this. Hit twice is from this, and hit 3 times, it's just gonna be 7. And you also can hit from here, right? This is this is not a game yet. But if you if you go from 0, you hit 0 times, right? This is where the first game begins. Okay, does it make sense? Okay, so basically, depending on how you look at this, so you can have go to the third card and you hit 0 times. So that will go to the fourth card, and the dealer gonna give you the fourth card, and the first game basically ends, right? And then you can choose to hit twice, and sorry, let me think. Yeah, and then the second game starts with the 5th card. That would be another different DP. So I don't want to draw it here; it's kind of messy already. But the point is that each of the subproblems are transitioning based on the number of gets you make, and they're transitioning. And each of these transition functions just defined using this. This is a transition function. Yes.
I have a question. When you decide not to hit, how can you transition to state 4? Why can't you stay in the same state? Because you're not changing anything.
Right. So if you so the question is that if you choose not to hit, right? If you have the third card, you choose not to hit, then how can you transition to the fourth card? Okay, the reason is because the dealer always gives you 2 cards. The dealer has 2 cards himself, right? The dealer has 2 cards for himself. And they're gonna give you 1 card. Now, this is the 3rd card, which is the card that the dealer gives you. But, wait a second. Okay, so, at this point, the game no one has been dealt with 1 card. At this point, like 1 card hasn't been dealt. 2 cards has been dealt. This 1 card is gonna give with the dealer. This card is gonna give this dealer, and this card is gonna give you. And but this point the game hasn't begun yet. So dealer, whatever you do, dealer will give you 1 card. So you actually choosing to hit, but I mean this choice is automatic. You understand? Like when you're not actually hitting, just
So like at card 4, if you choose to stand, it will be staying at stage 4.
yes.
Okay.
If you choose to stand, that's right. Yeah, it will stay at stage 4. Yeah, actually, it's kind of messy. Yeah, I didn't imagine it to be a little bit messy, actually. But yeah, I think it helps if you enjoy the game. But I don't see any. Okay. I mean that's the like what it gives like what it means to draw this kind of a directly synchronous graph. Just trying to imagine that you're jumping like from one state to another while using this kind of transition function. You're always trying to make the best choice looking globally using this transition function. So you're actually exhaustively trying all the possibilities each time when you're at a state, you exhaustively try each of the possibilities. Does it make sense? So so computationally, let's say what is like computationally. So you want to initialize a 1-dimensional array, right? So this array is just a DB table where you have let's say 52 elements in this 1-dimensional array. So the first time when you start this array, you want to get the base case, right? So the first 3 elements would be 0 of this array. Do you agree? Like the first 3 elements is the base case. So the first 3 slots of the array will just be 0. And after that, we want to start building the DB table. We want to use the for loop and exhaustively go over ij, where I is just the current position you play, j is just all of this inner loop. So there will be 2 different nested loops. One is the i's loop, the other one is j's loop. J indicates the number of times you hit for each of the I. And then, while you are doing the second loop, while you're within the second nested loop, basically you're updating the DP slot like from 0, like each time. You understand? Like each time you go over the i's loop, like the outer loop, each time you go over that loop, the inner loop is updating like the whole array every time. It's always maximizing it, so it's guaranteed that it will like eventually give you the maximum value.
So like the outer loop would be like from 0 to something?
From 0 to 51. Because
yeah.
outer loop basically gives you the
And like the inner loop would be like from 0 to I.
No, inner loop actually doesn't matter because the inner loop is just like number of times you guess. Inner loop is this.
Oh, okay.
So the number of times you guess to hit. That's the inner loop. So the times you hit is range from 0 to 52. Like you can hit at most as 52 times. Right? Does make sense. But you just need to like a little break, like a break function. If loop that if at the current moment you can't hit anymore, just break the loop. Right? But ideally it doesn't matter that how many like the loop with length of 52, it doesn't really matter like with a loop of 16 or something. Because the runtime complexity is just all of it. Yeah, that part doesn't change. So you can just have like a loop that's like just guessing like how many times you hit. Any question? You kind of imagine that what is the thing look like. Yeah. So the runtime complexity, since we have 2 nested loops, just would be all of square and square. Right. So that's also brings us back to that why we shouldn't ask that question. So whether you should hit or not, that would be like explanation. And yeah, I think so the reason why this is called a suffix problem is that you can use one single index to denote the whole subproblem you have. But that's not always the case because can you tell me what time is it?
5:45. Yeah.
Oh, it's 5:00.
45.
40, oh my god.
Yes.
Sorry, just 1 second. Yeah, that's not always the case. Like for the palindrome problem, at least it's gonna be 2 indices. So it's gonna be dpij, instead of just one single variable dpi. Yeah, but we don't have time to go over the palindrome problem. It's for this session. So, the palindrome problem is gonna be the third type of DP problem. So it's gonna be dpij, but this time is just suffix, and the previous one we have is suffix. And the previous problem is exactly the same as suffix. I mean, at least I think it's exactly the same as suffix, but I need to double check. But yeah, this is the suffix type of problem. And yeah, if you have understand this problem, I would say like it's DP is already like I would say halfway down already, but it's gonna take more effort later like to improve. But this is the suffix type. The IJ type is the harder one. Yeah, because it involves 2 different variables to denote the DP table. And you have to figure out what those 2 variables mean in each of the subproblem, like under the context of the problem. So yeah, that's also very, very hard. Yeah, but we don't have time to go over the palindrome problem. But okay, I'm just gonna leave a little, like see before we start next session. That the palindrome problem is just saying that you can have like any word, English word, like say gigs for gigs, right? This is an English word, but it's perfectly valid. So you can have 2 choices, right? I mean, so you're trying to find like a palindrome within this word. But instead of finding substring, right? Substring is basically mean the continuous strings, right? So say that gig, right? This word will be a substring of the gigs for gigs. Does it make sense? So that's a substring. But what we're trying to solve is the problem we're trying to work with is called a palindrome subsequence, longest palindrome subsequence. So it's finding a sequence instead of a string. So sequence can be not uncontinuous, which means that so E, S, E, this would be a perfect like palindrome sequence, but it wouldn't be a palindrome string because it is not continuous, right? So a lot of so let's say the interview questions would ask you what would be the longest palindrome substring question, right? That's type of question. So that problem is actually easy to solve because all you need to do is use 2 pointers, right? If you heard this technique called 2-pointer technique, so you update the position of the pointer and indicate where the string starts and ends. So the runtime capacity will just be n squared because you're using 2 loops and you try all of the possibilities of the possible substrings of this string. And then you check if that substring is actually a palindrome. If it is, just update the length of the longest palindrome you can have and then return the longest length at the end. So that's an n squared algorithm. But
wouldn't make it n cube?
Yeah, you have to check whether it's like palindrome or not, right?
Yeah.
Right, it's n cube, sorry. Alright. That's a quiz, sorry. Alright, it's gonna be n cube, but this case, we're gonna solve the problem that, I mean, it's arguably, it can be very short, but I mean, I'll give you that, it's n cube. Alright, but in this case, we're not doing like substring, right? We're doing subsequence, so you can have this kind of uncontinuous like strings extracted from the main string and form a new word, which is the x, and not x, I don't know. Okay, E as E. That's a palindrome. Okay, that's the hard part, and we have to use dynamic programming to solve it efficiently within run cube this time. So yeah, think about that, and we're gonna talk about that like next class, and we have to code it out. And before that, we'll also have to work through like which each of these steps means, and within the context of this IJ problem. Okay, but the implementation is already on the GitHub, and if you don't want to solve it, just look over that GitHub. So yeah. Also, the notes I left the notes on the GitHub, and the notes also like walk you through like how to solve this problem. I walk you through the computational graph there. Right. So have a good weekend. Thank you very much.